Hello and welcome back. With the chain rule and the product rule now done, we are ready to move on to the quotient rule. Quotient rule. All of the product rule concern multiplying functions. The quotient rule is going to concern dividing functions. So let's just first look at if we can already evaluate such a function where f of x equals 3x squared plus 5x plus 7 divided by 4 minus x. Let's see if we're equipped to handle such a thing. Well, to start off, what we want to do is we probably want to separate this into the product of two functions. We'll separate this into the 3x squared plus 5x plus 7 bit multiplied by the 1 over 4 minus x bit. Out of the way, we can now apply the product rule to take our derivative. So f prime of x will equal the derivative of this inside function. So 3x squared, that's going to be 3 times 2x, which is 6x term. 5x is going to go to 5 because the slope of that 5, and 7 is going to go to 0, so that's a wrap for that term. 1 over 4 minus x just stays, because remember, it's the derivative of this times the normal of that, plus the normal of this times the derivative of that. So let's go on to that other term there. Let's actually give ourselves some more canvas here to draw. So, just going to copy down the green function. 3x squared plus 5x plus 7. And now the derivative of that inside function. Well, what we notice is that if we say that u equals 4 minus x, then we could look at this as a composite function where we're looking at 1 over u. And we're trying to find the derivative with respect to x here. Well, the derivative with respect to u, because remember, if we're trying to do this, let's just call this function g for a second, dg by dx equals du by dx times dg by du. Well, g equals 1 over u, so dg by du, that term, right here, the dg by du, that's going to turn into minus 1 over u squared from the polynomial rule into u by dx. Well, the derivative of this term with respect to x is minus 1, since the slope is minus 1 of that. Minus 1. And if we multiply this out, that's going to be just plus 1 over u squared. But instead of writing u squared, we know what u is. U's 4 minus x, and that's what we write down. 1 over 4 minus x. This term gets a squaring, and we did that one in blue. Whoops. One over 4 minus x squared. Right there. Alright. So now we have to multiply all of this stuff nice and together. F prime of x equals 6x plus 5 divided by 4 minus x plus 3x squared plus 5x plus 7 divided by 4 minus x all squared. And then we'd have to simplify out our fraction at this point. We have to multiply each of these terms down here by a 4 minus x to get it up to 4 minus x squared on the bottom. And then we'd have to simplify everything out, and it becomes a bit of a long process. And it'd be nice if we could simplify things a bit. Well, let's just look at the case abstractly, because we could keep simplifying this right now, but we'll eventually get to our answer using just the regular rational rules that we're familiar with. Let's just consider the abstract case for now, where we have f of x over g of x. Well, what does this equal out to? We know from before that we could rearrange this as f of x times 1 over g of x. And we know that from our product rule, it's going to be f prime times 1 over g of x on one side. So when we find our derivative, d by dx, f of x over g of x, we're going to have f prime of x, because it's the derivative of that one, times the normal of that one, it's g of x. Then we have to add to that the normal of f of x times the derivative of 1 over g of x. Well, 1 over g of x derivative, we can look at this as a 1 over g situation. It's going to turn into minus 1 over g squared when you take the derivative of that. And then you have to just take the derivative of g with respect to x here. So you have to multiply it by g prime of x with respect to the inner function g. So we have the outer function, 1 over g, times the inner function, which is g. So 1 over g squared times g prime of x. That's what we're going to put in here. So g of x all squared. The minus sign came with it. And then we have to multiply by g prime of x. All right, we're almost done with our derivative, the quotient rule. All we have to do now is multiply this side by g of x down here and this side by g of x up here to get the same denominator. Now we shall write this out as f prime of x times g of x minus f of x times g prime of x, all divided out by g of x squared. So you technically don't need the quotient rule, because the quotient rule is just a combination of the product rule and the chain rule. Let's just look at one last example where now we have the whole chain rule. We have the whole quotient rule, I mean. So let's look at f of x equals 3x plus 5 cubed divided by 2x squared plus 4x minus 1 all squared. Well, this is going to be top function, and this is going to be our bottom function. So let's go ahead and take the derivative of our top function separately right here. So 3x plus 5 all cubed. I'm just going to use this arrow right here just to mean we're taking the derivative of it. This is never do this formally, but this is just something I do informally. So we have to take the derivative of the inside function, which has a slope of 3, multiply that by the derivative of the outside function, which is going to be 3, take this down, plop it out front, times 3x plus 5, and we have to take this down by 1, minus 1, which is 2. So then that simplifies out to 9 times 3x plus 5 all squared. All right. And how about the purple function? What's that derivative? Well, the purple function is 2x squared plus 4x minus 1. Take the special little derivative arrow. Let's put a little dx like that on top, just to imply we're taking the derivative here. So 2x squared here. Oh, this is all squared as well. So the derivative of the inside function, 2 times 2 is 4. So 4x, because this is the x squared goes to 2x, and 2 times 2x is 4x. Plus, well, the slope of 4x is just 4. Constant terms go to 0. And then the 2 comes out front here. And then we have to just repeat the entire inside. 2x squared plus 4x minus 1. And 2 minus 1 is 1, so it's to the, pardon me, to the first power. And that'll handle that. For this one, we are going to have this sort of 2 times 4x plus 4 times 2x squared plus 4x minus 1 situation going on. So now that we have our two derivatives, we can now use this right here, which is essentially on top. If we had a little plus sign here, this would be the product rule. But there's a minus sign for the function on the bottom when it takes the derivative, because 1 over g goes to minus 1 over g squared when you take the derivative with respect to g. All right. So now we have this written out in green. So let's write this out now in green again. F prime of x equals f prime, which is 9, is 3x plus 5, all squared. Multiply that by 2x squared plus 4x minus 1. And then we have to subtract that. Oh, I switched into doing the, you know what, we'll keep it color coordinated. Then we'll have from here 3x plus 5 cubed. Multiply that by the derivative of that inside function, inside my bad bottom, which is 2 by 4x plus 4 by 2x squared plus 4x minus 1. 4x minus 1. And then all of this, it's a big ol' fat division by the purple function, all squared again. Oh, I always forget that. So 2x squared plus 4x minus 1, and when you square, it becomes to the 4th power, which is just insane. Okay, so immediately what we can see here is that we could factor out one of these, because we have 2 right here, and we could factor out 2 of these because we have 2 over here. So that's what we'll do to make things easier on us. Now we'll get back into doing this. So 3x plus 5 squared, 2x squared plus 4x minus 1. Then that leaves us with 9 by 2x squared plus 4x minus 1 minus 2 by 4x plus 4. And I almost forgot the little g there. 3x plus 5. We don't have to worry about powers because we factored out 2 of them. Of course, we still have our denominator being, come on, expand this whole thing out. Yikes. Super large denominator. 2x squared plus 4x minus 1 to the 4th power. And this term and this term are going to cancel out, and that's going to leave us with a 3 on the bottom. Oh man, still have a little bit more to do. Now we have this 3x plus 5. It just, there's no easier way to do this. This is just always going to be that long and annoying process. Let's multiply this out. So the 9 goes into everything here. 18x squared plus 36x minus 9. And then this will be minus 2. I'm going to leave the minus 2 up front here first. 4 times 3 is 12, x squared. 4 times 5 is 20. 3 times 4 is 12. That's 12 plus 20, 32, x. And then 4 times 5 is 20. So that's going to be plus 20 right there. And now let's actually go back and do the doubling. So this is now going to be minus 24, minus 64, minus 40. Let's just write that down on top so we do not forget. 24, 64, 40. This is just so we don't have to keep making so much space here. It's just going to start getting out of hand. Minus 24 x squared minus 64x minus 40. Wow. Big. Hey, at least there's not as much to divide by at this point. Yeah, maybe this one would have been better if I would have did it as a multi-step recording. But whatever, we're here now. We're almost at the end. Very, very close to the end. These quotient rule problems can really get long and annoying when you're working with polynomials. The nice thing, though, is that these sort of annoying polynomials kind of go away when you start to focus on more and more important derivatives, when we get to trig and exponentials. So 3x plus 5 squared. All we have to do is simplify this inner bracket, and we're golden. 18 minus 24, so minus 6. Minus 6, x squared. 36 minus 64. We are looking at a grand total of 28 there. Negatively. Minus 9 minus 40 is minus 49. I'm going to be skeptical of factoring in that term. We could look for it, but I think we've already spent long enough on this polynomial, and we could declare this finally as our derivative, f prime of x here. And that is just one application of the quotient rule. I'm going to try to refrain from putting that long polynomials together like that into a quotient rule. And that's a wrap for this. Hope to see you next time when I cover trig derivatives.